Are atoms real?
Nobody has ever seen an atom. Yet scientists count them. They even build wire models which show how atoms are arranged in space. But if atoms can be counted and located and weighed, then surely atoms are real.
Atoms real? But of course. If the chap who asked the question had only said, "Are flying saucers real?" we might have had something to argue about. But atoms, after all, this isn't 1810 or 1910, this is today.
But you can't see them.
What of it? You can't see air, but you can breathe it and feel it pushing against you on any windy corner. Things can be real without being visible. But come to think of it, we're being a bit superficial. Our question, "Are atoms real?" invites us to do some hard thinking about the word real and about what the scientist knows about atoms. After all, the word real is one of the most important in the language and more than a little tricky. We all use it and have a feeling for its meaning, but there isn't any clear and generally accepted definition. All of us will agree, I suppose, to the importance of a proper sense of reality. The feeling for the distinction between reality and illusion, reality and fiction, reality and myth. This is the mark of sanity, maturity, and education. An insane person is one who lives in a world of delusion, out of touch with reality, because he cannot face it. A child who daydreams over much and spins fantastic stories has a child's imperfect feeling for reality. The ignorant, superstitious, and credulous are like the child in their imperfect sense of reality. Among primitive men, fact and fancy have always been fantastically intertwined. The archaeologists tell us that in the ancient civilizations of Egypt and Babylon, the sharp distinction we draw today between dreams, hallucinations, and normal sight was not generally drawn, nor was there a clean separation in thought between appearance and reality. It was the Greeks who first interpreted the world directly revealed by our senses, the world of light and color, sound, taste, smell, and touch, as a world of appearance behind which there must be a world of reality. From this point of view, we can regard science, which began with the Greeks, as an attempt to lay bare the real world behind the camouflage of appearance. You see, a rod thrust obliquely into the water appears to be broken at the water surface, but in reality it is as straight as ever. The sun appears to rise in the east and sink in the west. In reality, according to Copernicus and Galileo, the sun stands still. It appears to move only because we see it from a moving earth, which spins on its axis as it slowly swings around its sun-centered orbit. Reality suggests truth. In fact, truth is sometimes defined as agreement with reality. Thus, the scientific exploration of reality is a part of man's great quest for truth. And the scientific way of getting at reality is his most powerful aid in the search for truth. From this point of view, the deeper the scientist goes in his exploration of the physical universe, the more he understands, the closer he is to reality. If the real world is what lies behind the world of appearances, then the world of atoms, electrons, photons, and electric waves disclosed by modern science can well be regarded as the real physical world. So let's look at this world of atoms. Physicists and chemists believe that matter is granular, that it is composed of particles. We call them atoms, too small to see individually even in a high-powered microscope. They tend to unite in small, tightly knit groups called molecules. These models crudely represent atoms joined together into molecules of different kinds. Sometimes the atoms remain single. In this case, we call them single atom molecules. Please note, the distinction between atoms and molecules is, for many purposes, unimportant. Do not worry if I sometimes seem to use the words interchangeably. A sample of any pure substance consists of an enormous number of molecules or atoms of the same species. They are conceived to be in perpetual, chaotic, haphazard motion. We call this invisible motion of invisible particles thermal agitation. The energy of this motion is heat. The intensity of the motion is measured by temperature. As the temperature rises, the pace of the motion is increased. As the temperature falls, the motion slows down until, at the absolute zero, 460 degrees below the ordinary Fahrenheit zero, to all intents and purposes, it ceases. This conception of matter and heat helps us to understand the three fundamental states of matter: solid, liquid, vapor. In solids and liquids, the molecules are huddled together, whereas in a vapor or gas, they are relatively far apart on the average. Solids and liquids are held together by strong forces of attraction which atoms and molecules exert on each other when in contact. In a vapor, on the other hand, the attractive forces are unimportant. Most solids are crystalline. Whether the crystals are small and mashed together, as in this piece of granite, or whether they are separate, as in these other cases, this is quartz and rock salt. In a crystal such as rock salt, the molecules form a regular pattern, like the cells of a honeycomb. Each atom and molecule is bound to a fixed position by the attractions of its neighbors. The pattern of this structure determines the natural external shape of the crystal and the shapes of the pieces formed when it is broken. Let us now try to imagine what goes on inside a solid as it is heated up. Let me show you a crude model of a few atoms or molecules in the interior of a solid at the absolute zero. Each rests at its fixed equilibrium position. As heat is added, the molecules are set into vibration. At higher temperatures, the pace of the motion increases until finally it disorganizes the whole structure. The attractive forces are no longer able to hold the molecules near their home bases. The material loses its definite form and melts. It now forms a liquid that accommodates its shape to that of any containing vessel. This is what happens when we melt a candle. In the case of a liquid, the binding forces, though insufficient to maintain a solid structure, are still able to keep the molecules huddled together in a compact mass. If a molecule on the outside of a drop of water is given an accidental shove toward the surface, the combined attractions of its neighbors are usually able to prevent its escape. Occasionally, however, the accidents of the thermal dance will give a surface molecule a much larger push than usual, with the result that it does escape from the drop into the surrounding air. The molecule evaporates. It enters the vapor state or gaseous state. In ordinary air or steam or any gas, the molecules are far apart on the average. They collide with one another, but most of the life of any molecule is spent so far from its neighbors that it lies beyond the range of their attractive forces. The molecules are free, aside from occasional collisions. This is only a suggestion of the way in which the molecules move. Actually, the molecules in a gas move at high speeds, in straight lines, interrupted occasionally by a collision. Because a gas, in comparison with a liquid or solid, is a thin population of molecules, the gas has no cohesion, and it expands to fill any container in which you put it, like this. I've been describing very briefly the three states of matter: solid, liquid, and gaseous, in terms of the atomic molecular theory. In other words, I've been giving you glimpses of the world of atoms. Let me assure you that such pictures shed a flood of light on the behavior of matter when it is heated or cooled, compressed or expanded. The atomic picture is equally useful in the interpretation of chemical reactions. Each element is conceived of as composed of a corresponding species of atoms. When two elements unite to form a compound, the atoms of the elements are combined to form molecules of the compound. Water, for example, is a compound composed of molecules, each of which contains two atoms of hydrogen and one of the element oxygen. This conception finds thousands of confirmations in the detailed study of chemistry. There are no chemical or physical facts with which it does not harmonize. Moreover, the atomic theory has served not only to explain the already known facts about the physical and chemical transformations of matter, it has suggested an enormous variety of experiments that in turn suggest new facts about atoms, their structure and properties. In the light of our constantly growing knowledge of the details of the world of atoms, we are able to understand such things as why glass and alcohol are transparent while iron and copper are not, why a clean surface of silver gleams, why a mixture of gasoline and air explodes violently when lit by a match. We understand, too, why there are 91 elements found in nature that have atoms lighter than uranium, and no more. Why radium, thorium, and uranium are radioactive, while oxygen, nitrogen, and iron are not. How it is that the sun has been able to pour out vast quantities of heat for billions of years and does so still. These are deep questions. 50 years ago, one would hardly have dared ask most of them. Today, we ask them, and we know the answers. And knowledge of the world of atoms brings power as well as understanding. Power to control chemical processes, to create a vast variety of new and useful materials, such as nylon. The technological achievements of modern America rest firmly on our understanding of the world of atoms. In fact, if the world of atoms is not real, it would seem that American industry is built on an illusion. But perhaps you want to remind me at this time that the world of atoms is a world of theory. If you are a hard-boiled realist, you may have a deep instinctive distrust of theory. You may say, is it not true that the world of atoms is an imaginary world dreamed up by scientists to explain chemical experiments and chemical processes? No matter how useful these ideas are, how can you be sure that atoms are real in the same sense that chairs, trees, and houses are real? Isn't it true that in many cases there are several theories that fit the same facts? Haven't the scientists again and again had to change their theories? Didn't Einstein's idea of relativity upset a well-established and useful theory of motion? Did it not even upset our ideas of time and space? How then can we be sure that the theory of atoms will not be swept away by some future scientific revolution? These are hard questions, though some of them have obvious answers. To be sure, the world of atoms is a world of scientific theory, and scientific theories do change constantly. But the point to remember is this: when a fundamental theory with a wide range of applications is replaced, the new theory must explain all the facts and relations explained by the old theory. Therefore, it inevitably resembles the old theory in many respects. And by our present theory of atoms, we are able to tie together a vast quantity of facts. Therefore, we can be sure that any new theory that takes its place must preserve the truly essential features of our present one. So as science makes new discoveries about the structure of matter, we can expect subtle modifications of our present theories. But the abandonment of atoms is unthinkable. That would make nonsense of modern physics and chemistry. Mature science never destroys itself. It may change its clothes, but not its skeleton, and the atomic idea is part of its skeleton. Moreover, We have certain crucial types of experiment that point so directly toward the reality of atoms that the evidence seems truly overwhelming. I want to show you several direct proofs of atomic and molecular reality. First of all, there's the Brownian motion. You have to use this to see it. Under the lenses of this microscope are fine particles of a mineral suspended in water, nothing else. The particles do not sit still. They perform an unceasing irregular motion, as if they were alive. They are not alive. All such particles execute this Brownian motion if they are small enough. Take a look. You see particles of various sizes swimming in the water and drifting about. Look carefully at the smaller particles. They move somewhat irregularly and sometimes change their courses. They move because they are small enough to share in the general temperature agitation of the water molecules that surround them. They are jostled by the invisible water molecules, just as a ship at sea is jostled by the waves about it. The movement of a large ship is much less violent than that of a small boat. So here, the large particles are less active. This is thermal agitation made visible. These particles are not molecules, they're bits of powder. But their motion proves the existence of a concealed thermal agitation. They give striking confirmation of the atomic conception of the nature of matter and heat. But I can do better than this. For example, today it is a commonplace matter to record individual events in the atomic world. This recording is made easy by the existence of radioactive atoms. Atoms that spontaneously explode from time to time. As they explode, such atoms throw off high-speed projectiles. There are several kinds, but one variety of these projectiles is the alpha particle. This is an atom of helium that carries a double electrical charge. You see, when an alpha particle is ejected into the air by a radioactive atom, it passes through thousands of molecules and knocks chips out of many of them. When a molecule is struck by a flying alpha particle, it is commonly broken into two parts, one carrying a positive charge and the other negative. These charged particles, fragments of atoms or molecules, are called ions. The process by which they are formed is called ionization. Now one can observe the production of ions by alpha particles or other kinds of particles, for that matter, in several ways. The simplest is to make use of the fact that any gas containing an appreciable number of ions is a temporary electrical conductor. You can send a pulse of electrical current through it, amplify the pulse, and use it to trigger off a loudspeaker. This is the principle of the Geiger counter, which is used by prospectors hunting for uranium and for many other purposes. This instrument makes a clicking noise when it is in the presence of radioactive rays or the ever-present stray cosmic rays. Each of these clicks records an individual atomic explosion producing an alpha ray or a stray cosmic ray. As the ray enters the instrument, it triggers off a pulse of current which clicks in the loudspeaker. Here's a block of uranium. If I bring this close to the mouth of the Geiger counter, it goes crazy under the influence of the alpha particles which are constantly being emitted from the surface of the uranium. These clicks mean flying particles moving with enormous speed, particles ejected by the spontaneous explosion of atoms of uranium. Notice, you can't see an individual uranium atom or a flying alpha particle, but you can hear one. Or do you object to saying that you have heard my voice when it comes to you over a telephone wire or by the way of the unspeakable complications of a television recording? This is pretty impressive proof of the reality of atoms, but we can do better. We can see the track made by a flying alpha particle. As these particles fly through the air, each leaves behind it a trail or track of positive and negative ions. These ions are as invisible in an ordinary microscope as the alpha particles themselves, as invisible as all individual molecules, atoms, or subatomic fragments. But there are ways to convert the invisible trail into a visible one. One way, developed by C.T.R. Wilson, is to allow the ion trails to form in chilled, moist air. For example, let me blow on this piece of cold, dry ice. You see that the moisture of my breath forms a cloud when it's chilled. The chilling creates a fog by condensing water vapor into a multitude of tiny, visible drops of water. If there are ions present in such moist air, the water drops condense on them first. If these ions are distributed along the trail left by an alpha particle, the water droplets form a line or track where the alpha particle passed by. To observe these tracks, you can build a glass-enclosed cloud chamber, similar to this one. Inside, the tracks are easy to photograph. They frequently tell interesting stories. Here, for example, is an ion trail photograph showing a pattern of alpha tracks from radioactinium. Here is a similar group of tracks from radioactive polonium. Here you can see what happens when the tracks form in the field of a large electromagnet. The bending of these tracks is due to the interaction of the charge carried by the alpha particles and the magnetic field. It proves that the particles carry positive electric charges. Now suppose the radioactive material you use as the source of alpha rays is itself a gas mixed with the air. In this case, the spontaneous explosions which eject the rays can start anywhere in the chamber and may move in any direction. Here is a single track from an atom of radon in such a chamber. In the case of thoron, another radioactive gas, the explosions occur in pairs in rapid succession. Hence, we observe pairs of trails diverging from a common point. Let me inject a little thoron into this cloud chamber. At first, you see a cloud formed by confusion of ions as the gas enters. Then, as the gas distributes itself out a bit, you can see pairs of tracks. Each pair of ion trails is automatically transformed into a pair of water drop trails, sharply defined at first and then slowly fading. And now, if you still have a lingering skepticism about the reality of atoms and molecules, you might ask yourself the question, what are those tracks? What makes the Geiger counter click? How can such effects occur if matter is not composed of atoms?
Professor Campbell has left us with a question. Did he do it just for rhetorical effect? I don't think so. I believe he really wanted you to decide whether you wanted to call atoms and molecules and ions real or not. Here's what I would say in reply to his question. I take it that you and I and Professor Campbell think that apples are real. Now, an apple is at a certain place there in space. It occupies a certain volume and it has weight. What Professor Campbell has told you about molecules and atoms shows that they are in these three respects just like apples. Well, not exactly so, but very, very nearly so. So I would say that molecules and atoms are as real as apples. And that goes for ions too. By the way, if you were to deny that apples are real, that would simply move the discussion to another plane. But on that plane, we should still hold the same view of atoms as of apples, I believe. In the cloud chamber pictures which Professor Campbell showed us, we saw tracks being made, which consisted of illuminated water droplets. They were very much like the luminous tracks made at night by a tracer bullet, or by a meteor, a shooting star penetrating our atmosphere. So, seeing this, we say that some kind of small object, which someone thought of calling an alpha particle, behaves like a tracer bullet. We can collect many of these particles, and we find that what we've got is helium gas. So then we say these particles are constituents of helium gas, that is, helium atoms. Moreover, they must be electrically charged in order to be moving on curved tracks in the cloud chamber, as we have seen. Hence they are, speaking more correctly, helium ions. Gas molecules are real because we can find out how many they are in a cubic inch, how fast they fly, and so forth. Atoms are real because we can not only count them off, we can locate them in space as they build up a crystal lattice, like these. Alpha particles are real because they behave like little bullets. These three classes of things, molecules, atoms, and ions, are really small chunks of matter, sometimes electrified, sometimes not, and differing from other chunks of matter, such as apples, simply in being so very, very much smaller. So my own answer to Professor Campbell's question, which I give you for what it's worth, is if apples are real, then atoms are real too. And the same goes for molecules and also for ions. But note that Professor Campbell didn't mention today any other kind of particle. Are electrons real? Maybe they are, maybe they're not. I believe they are. But that poses another question.
This is National Educational Television.